Hello, good friends. I have a toy I'd like to show you today. As you can see, it's a box that's got a square shape to it, and with it goes a set of 4 triangles. They're all the same size and shape. They're all right triangles. That is, they have a right angle on them, and the box happens to be made just so that the 2 sides that make up the right angle, if you add them together, are equivalent to the side of the box. You can see that by putting 2 of the triangles this way. The 2 sides add up together and they fill up the length of the side of the box. The game consists in looking at ways that you can arrange the triangles inside the box and see what that can show you. I'd like to show you 3 different configurations of that sort. Here's one of them. It's an easy one to think about. You put the right angles of each triangle in a corner of the box, and you alternate them around the edge of the box in this way, and you come up with this shape. Isn't that pretty? Another thing you can do, you can put the triangles together to make a rectangle, and here's one way that proves interesting. And if you do it a little bit differently, you can produce 2 squares of different sizes with the triangles. Now, whether you realize it or not, we just proved the Pythagorean Theorem in 2 different ways. What do you think about that? Most of you probably ran into the Pythagorean Theorem sometime in school, but perhaps some of you didn't, and in any case, a good many of you may have forgotten what it is. So let's review a bit. The Pythagorean Theorem is named for Pythagoras. He was an interesting dude. He was a philosopher and a mathematician. One thing he said as a philosopher has kind of stuck with me, and I think it's worth thinking about. He said that as soon as people need laws to govern them, they prove themselves unworthy of freedom. Think about that one. He was born and lived the first part of his life on the island of Samos in the Aegean Sea. Samos is very close to Ephesus in what is now Turkey. Besides mathematics, Pythagoras was also very interested in music, and in fact he's sometimes called one of the fathers of music. He was into geography and astronomy and a whole bunch of other things. And he founded a famous school. Some people think it was his students rather than himself who formulated the Pythagorean Theorem, but in any case, it has his name on it. And what is the Pythagorean Theorem? Well, one well-known statement of it says that the square upon the hypotenuse of a right triangle is equal to the sum of the squares upon the other 2 sides. With any scientific definition, it's a good idea to be very sure that you have your terms defined so that you know you're talking about the same thing as other people. So here is a right triangle. The right angle is this one, and the side opposite the right angle, the one that doesn't touch the right angle, is called the hypotenuse. So that's what it means when it says the square of the hypotenuse. The other 2 sides are, of course, the ones that form the right angle. And by convention, when geometers talk about these, they call the 2 sides that make up the right angle A and B. The hypotenuse they call C. So a lot of you probably ran into the theorem and may remember it in the algebraic form, where you write A squared, and the squared is, of course, the way we read, a little 2 that's raised up above the letter. And it means that the amount that the letter represents, in this case A would be this amount, is multiplied by itself. So if you multiply A by itself and you multiply B by itself, the sum of those 2 amounts will be the same as multiplying C by itself. It's a very useful way to formulate the theorem for many purposes. However, I'm pretty sure that when it was first developed, they had something much more tangible or physical in mind for the square upon the hypotenuse or the square upon the other 2 sides. I think they had something like this. Here's a square, and no matter how you turn it, its sides are the size of A. So we can call this square the square of A. And here's the square of B, also made just the right size to match the longer side of the 2 that make the right angle. And here is the square of C. This is the square upon the hypotenuse. So what the theorem is saying is that this square is equal to these 2 squares together. So you add up what is the size of these 2, and it comes out to the same as the size of this one. And that's the Pythagorean theorem. Once you understand it this way, you can see a little more clearly how our game was proving the Pythagorean theorem. If you look at this configuration, you can see that this little square down here is the square upon the shorter of the two non-hypotenuse sides. And this bigger one here is the size of the square upon the other non-hypotenuse side. So the four triangles don't change shape and the box doesn't change shape. What's left over from the four triangles out of the box is exactly the quantity a squared plus b squared. And as we saw earlier, the same can be said if you move the rectangles around and do it this way. We have the squares upon the two sides that are not the hypotenuse, and they fill up the box. Or we can, as we also saw, arrange the triangles around the box this way, and now we can fit the square upon the hypotenuse in the middle of it. And then, of course, since we still have the same four triangles in the same box, the amount that's left over is equivalent to the square upon the hypotenuse. Just as we saw that with the other configuration, the amount that was left over was equal to the squares upon the other two sides. Isn't that beautiful? Now, several of you had asked me, what does this have to do with linguistics? And I have two answers to that. One of them is, does everything in the universe have to have something to do with linguistics? Probably not. The second answer is, you know what, if we're going to talk about anything, linguistics is going to enter into things, because linguistics is the science of how we talk. Also, I think we can find some parallels or some ways in which this exercise in practical geometry is relevant to linguistics in other ways than we think. I first ran across this way of proving the Pythagorean theorem in a piece written by Aldous Huxley. And it's a piece in which he describes a young man who is some sort of a genius. At first they think he might be a musical prodigy, but he changes his mind in the part that I'm going to read to you. This is fairly long, I gotta warn you, but I encourage you to just hang in there. It's not going to be too bad. The author was in an upstairs part of the house in Italy, and two children, Guido and Robin. Guido's a little older than Robin, and Guido's the one they suspect of being a musical prodigy. Were playing in the garden, in the patio down below. Knowing by experience, says the author, that when children are quiet, it generally means that they're absorbed in some delicious mischief. I got up from my chair and looked over the balustrade to see what they were doing. I expected to catch them dabbling in water, making a bonfire, covering themselves with tar. But what I actually saw was Guido, with a burnt stick in his hand, demonstrating on the smooth paving stones of the path that the square on the hypotenuse of a right-angled triangle is equal to the sum of the squares on the other two sides. Kneeling on the floor, he was drawing with the point of his blackened stick on the flagstones, and Robin, kneeling imitatively beside him, was growing, I could see, rather impatient with this very slow game. "Guido," he said. But Guido paid no attention. Pensively frowning, he went on with his diagram. "Guido!" The younger child bent down and then craned around his neck so as to look up into Guido's face. "Why don't you draw a train?" "Afterwards," said Guido. "But I just want to show you this first. It's so beautiful," he added cajolingly. "But I want a train," Robin persisted. "In a moment. Do just wait a moment." The tone was almost imploring. Robin armed himself with renewed patience. A minute later, Guido had finished with both his diagrams. "There," he said triumphantly, and straightened himself up to look at them. "Now I'll explain." And he proceeded to prove the theorem of Pythagoras, not in Euclid's way, but by the simpler and more satisfying method, which was, in all probability, employed by Pythagoras himself. And here comes the description. He had drawn a square and dissected it by a pair of crossed perpendiculars into two squares and two equal rectangles. The equal rectangles he divided up by their diagonals into four equal right-angled triangles. The two squares are then seen to be the squares on the two sides of any one of these triangles other than the hypotenuse. So much for the first diagram. In the next, he took the 4 right-angled triangles into which the rectangles had been divided and rearranged them around the original square so that their right angles filled the corners of the square. The hypotenuses looked inward, and the greater and less sides of the triangles were in continuation along the sides of the square, which are each equal to the sum of these sides. In this way, the original square is redissected into 4 right-angled triangles and the square on the hypotenuse. The 4 triangles are equal to the 2 rectangles of the original dissection. Therefore, the square on the hypotenuse is equal to the sum of the 2 squares, the squares on the other 2 sides, into which, with the rectangles, the original square was first dissected. That's where Huxley's description of Guido's proof ends. But I'm going to read a bit more. It's relevant. In very untechnical language, but clearly and with a relentless logic, Guido expounded his proof. Robin listened with an expression on his bright, freckled face of perfect incomprehension. Treno, he repeated from time to time. Treno, make a train. In a moment, Guido implored. Wait a moment. But do just look at this. Do, he coaxed and cajoled. It's so beautiful. It's so easy. So easy. The theorem of Pythagoras seemed to explain for me Guido's musical predilections. It was not an infant Mozart that we had been cherishing. It was a little Archimedes, with, like most of his kind, an incidental musical twist. Treno! Treno! Shouted Robin, growing more and more restless as the exposition went on. And when Guido insisted on going on with his proof, he lost his temper. Cattivo Guido, he shouted, and began to hit out at him with his fists. All right, said Guido resignedly. I'll make a train. And with his stick of charcoal, he began to scribble on the stones. I looked on for a moment in silence. It was not a very good train. Guido might be able to invent for himself and prove the theorem of Pythagoras, but he was not much of a draftsman. Guido, I called. The 2 children turned and looked up. Who taught you to draw those squares? It was conceivable, of course, that somebody might have taught him. Nobody. He shook his head, then, rather anxiously, as though he were afraid there might be something wrong about drawing squares, he went on to apologize and explain. You see, he said, it seemed to me so beautiful, because those squares, he pointed at the 2 small squares in the first figure, are just as big as this one, and indicating the square on the hypotenuse in the second diagram, he looked up at me with a deprecating smile. I nodded. Yes, it's very beautiful, I said. It's very beautiful indeed. An expression of delighted relief appeared on his face. He laughed with pleasure. You see, it's like this, he went on, eager to initiate me into the glorious secret he had discovered. You cut these 2 long squares, he meant the rectangles, into 2 slices. And then there are 4 slices, all just the same, because, I ought to have said that before. Because these long squares are the same, because those lines, you see. But I want a train, protested Robin. Leaning on the rail of the balcony, I watched the children below. I thought of the extraordinary thing I had just seen, and of what it meant. Notice that what Huxley showed to us was different from what I showed to you first. In particular, the order of things was a little different. I started essentially with a square already made and the triangles, but in some sense I started with the triangle, multiplied it 4 times, and then built a box that was the right size to fit. Then from there, I showed how the triangles could fit in the square so that the leftover part was the size of the square upon the hypotenuse. Then afterwards, I showed how the triangles could be fit into rectangles and the rectangles arranged so that you could also see that what was left over of the big square was the shape and size of the squares upon the other 2 sides. Huxley's order was backwards from that. He started off with the square and then divided it by his intersecting lines into the rectangles and the two squares on the other two sides. Only later did he get to the triangles at all and move them around to show how the square of the hypotenuse also fits into the big square, the original square. So he didn't go about the proof in the same order that I did. Does that matter? Well, it depends on what your purposes are, what you're doing it for, what you need to prove, or what you need to show. For many purposes, yeah, it's the same proof. There are many other proofs of the Pythagorean theorem. It's probably the most proven theorem in the world. Some very interesting ones. Euclid's, of course, is the most famous, but then Einstein made another one, and he's famous even if his proof isn't as famous as he is. Even James Garfield, who was one of the presidents of the United States, made one. About all I know about Garfield was that he invented this proof of the Pythagorean theorem, and very soon after he was elected in the 1880s, I think it was, he was assassinated. One of 4 American presidents that were assassinated. I don't think his having invented the proof had anything to do with his being assassinated. Another thing probably worth commenting on is an awkwardness that I noticed in Huxley's writing that stemmed very clearly from the fact that he was not using any one word to mean a side of the right triangle that touches the right angle. In Spanish they have such a word, and in fact we have it in English. It comes from Latin. It's cathetus, and more than one cathetus is called the catheti. So there are 2 catheti in every right triangle. Huxley probably knew that word. He was a very erudite man, but he chose not to use it, and he probably chose well. But it was surprising to me how often in his exposition he had to stumble over the fact that there was no handy name for a cathetus. When you want to talk about something and you don't have a name for it, it's hard to talk about it. That is linguistically a very relevant fact. Here's some other points for linguistics. First one is that what one person says is not necessarily what the other person gets, even when the communication is successful. Huxley successfully communicated to me this way of proving the Pythagorean theorem, but what I remembered, was not exactly what he showed me. Here's a second one. Finding one way to get to a result does not mean that is the only way it can be or has been done. Too often we think, oh, I see something, that's the only way it can be done. Don't be so sure. Another point, the way you learned it, the way you've practiced it, is going to be the easiest way for you, at least at first. And it may be that your way is quite difficult for somebody else. That's linguistically relevant. Sort of summing up several of those ideas, linguistics really needs to cover not just the final result, but how you got there, what thinking processes you used to get there. You may be expressing a universal truth that's provable in many ways, but which way you go about proving it is linguistically important. This I don't know how to emphasize quite enough, but I'll try. We have to be really careful of the notion is the same as, is equivalent to, because it always depends for what purposes, in what circumstances are we attributing equality. And what looks at first as perfectly equal may not be. I told you that these triangles are equal. Well, they are. They're effectively identical. But this one has a mark on it that this one doesn't. And they can't occupy exactly the same space. Much of mathematics seems to consist in ignoring this in judicious ways and treating as completely equal and mutually substitutable things that aren't necessarily so. Very often linguists have tried to do the same thing, and it's a dangerous game. A final point that I'd like to make, remember Guido's response when he discovered Pythagoras' theorem. Do you remember what it was? He was rejoicing, he was happy, he was over the moon at having discovered something so beautiful. And he kept saying that. It's so beautiful, it's just beautiful. It's about as far from a self-centered or even a self-aware viewpoint as can be. He's not sitting there thinking, oh, look how smart I am, how intelligent I am. He's just thinking, oh, that is so beautiful. He's totally focused on what he's investigating, what he's studying, what he's figuring out. And that seems to me an admirable attitude, a very humanizing and ennobling attitude. I remember from my childhood a poem of Robert Louis Stevenson's that goes, "The world is so full of a number of things, I'm sure we should all be as happy as kings." A lot of people don't realize it, but Stevenson was reflecting a proverb of Solomon's. Solomon says, "It is the glory of God to hide a matter, and it is the glory of kings to discover it." I think of this verse as the Magna Carta for science. God has hidden stuff all over the whole universe for us to discover. And that shows us what kind of a God he is. That's what it means to say the glory of God. What shows out his actual character is the nature of the things that he hides and how he hides them from us to give us the pleasure of learning about it. And what does it do for us? It's the glory of those who discover those things. It shows what kind of people they are. And as we focus on what we can discover and look at it, it ennobles us. It's a kingly thing to do. And that, I think, is what Guido was experiencing. And I think that as we learn, the more we can keep that attitude of Guido's, of loving what it is that we learn, we will do well. I'm going to finish by showing one more way to prove Pythagoras' theorem. We can arrange the triangles in a way we haven't looked at yet, so that their hypotenuses are the ones that form a square, and the triangles themselves are turned inwards from the hypotenuse. The square that's formed by the hypotenuses, of course, is the square upon the hypotenuse. And when the triangles are turned inward from that square, they form another square. I'll just call it a new square. If you want to know its size, each side of it is b minus a. The four triangles plus the new square are equal to the square upon the hypotenuse. But you can arrange those same four triangles plus the new square in this other way. And when you do that, you can see, oh, that is the sum of the other two squares. That's b squared plus a squared. And once again, you've proven the square upon the hypotenuse is equal to the sum of the squares on the other two sides. So I just have a question for you. Isn't that beautiful?